Okay, let's go on page 35 when we're done. This is a 0-point lesson, meaning that it's not officially a section in AP Classroom or anything, but we talk about these things in the next couple of lessons. This isn't a reteach. You haven't seen this before, but I don't think the lessons do a good enough job. I feel like we need to see it separately first so that we can make a little bit more sense of it. It's not difficult. It's just new and maybe kind of weird to you. And this is going to require a lot of graphs. You see one graph on your paper, right? So I'm going to use Amplify, which is really Desmos activities, but it's a long thing. Desmos is owned by Amplify, and the Desmos calculator and the Desmos activities apparently are owned by two different people. I don't get it. But anyway, I'm going to assign them to you when we're done. That way you can go back and look at them, but I didn't want your notes to be 10 pages long because I needed to put a bunch of big graphs in there, all right? So I will assign it to you. You don't have to go do anything, but if you're looking at your notes, you're like, I don't even know. It goes with graphs that will be, and I will put a little link. I haven't gotten that far yet, but I'll put the link right here at the bottom of the calendar day and you just log in with your district Google stuff and you'll be able to see the graphs if you need to. If you don't want to go back and look at them, that's fine too. Okay. So we're going to talk about limits. Now we've already talked about limits a little bit, right? We talked about like the limit as x approaches infinity of f of x, right? And that is end behavior, right? Yeah, end behavior in our limit notation. That's right. Now, we're going to look at one- and two-sided limits today. Now, technically, our end behavior, when we're heading to the infinities, that's one-sided because I can't get on the other side of infinity, right? But if I'm heading to something other than infinity, so if you look at here, this one, I'm heading to 2. We'll talk about the little minus sign in a minute. But that's more what we would call middle behavior, which I'm putting in quotes here just because that's not really a thing. But I think if we have end behavior, middle behavior makes sense, right? It's the stuff that's not at the ends. Not necessarily directly in the middle, but middle-ish. So since I can approach a number from both sides, I can approach from the left or the right, then we have left limits and we have right limits. So a limit from the left, if the value of f of x, so if the output value, the value of the function, approaches a unique number as x approaches c. Now, c is just some number that's not infinity. So c could be 5, 6, -2, whatever. From the left, that's what this notation is. As x approaches c, and that little minus sign is like up where an exponent goes, but it's not like c to the negative power. That doesn't make any sense. It's just how the notation works, right? So like if you look here, 2, this would mean 2 from the left. That's what that is right there. If we have a limit from the right, so again, the value of the function, our output value, approaches a unique number as x approaches c. It says left again. I think I'm a victim of copy and pasting. This should say right, or it doesn't make any sense. From the right, that's what the little plus sign means. So the little plus sign means we're coming in from the right. The minus sign means we're coming in from the left. Okay. So let's look at this example here. We have these equations. We're going to approach 2 from the left. As x approaches 2 from the left, I'm going to drag along my function. Am I ever actually going to make it to 2? You sure about that? Yeah. Well, yeah, but does my function make it to 2? Like I can make it to 2. I'm sorry, I asked that badly. I can make it there. Does my function make it there? No, because it's open, right? Okay, so as I come from the left, it's open there, right? So 2 is not an x value on my graph. But my y value all along is -1. And I know it sounds weird that we're approaching it when we're already there. We're going to clear that up in a minute. Sometimes when we approach things, we make it there. Sometimes we just approach it. But I'm literally already at -1. So if I had a value at 2, it would be -1, right? That makes sense? That's what I would end up at. So my limit is -1. When I approach 2 from the right, what do you think my limit is? 1, +1. Okay, does that part make sense? Okay, So we're going to watch like a little 4-minute video that does a very good job of explaining limits and how they work. Way better than me, yes.
In a general sense, limits allow us to determine what value a function is approaching when we use a particular input. Not necessarily what the function gives us as an output, but rather what value it's getting arbitrarily close to. Let's explain limits using an analogy. Suppose you are watching TV and start getting a massive craving for pizza. Fortunately, you just happen to have some leftover pizza in the kitchen. So you get up from the couch and start heading towards the fridge. In this instance, if someone were to describe where you are going, they would say you are approaching the fridge. They would be confident in their description because as you keep walking, you are getting closer and closer to where the fridge is located. This example is the same thing we want to do with functions. When we take the limit of a function, we are describing where they are going. Let's see an example of this with the function 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to the number 2. Let's see this by using some inputs like 1.9, 1.99, and 1.999. When I use these, I get values such as 9.83, 10.8803, and 10.988003. From these values, it appears that the function is approaching 11. So we say that the limit of the function as x approaches 2 is 11. Remember, what I'm really saying here is that we can get arbitrarily close to the number 11. I just have to pick values that are sufficiently close to 2 in order to do it. Now at this point you might be thinking, that's fantastic, but couldn't you have also found the limit simply by plugging 2 into the function? Wouldn't that also give you 11? In this instance, the answer is yes. But the focus with the limit should be on what value it's approaching, and there are some functions where you simply can't plug in a number to find the limit. In other words, they are not always the same. Let's cover this by going back to our pizza analogy. Like before, you've been struck with a craving for pizza. So you are headed towards the fridge for a quick snack. Now, in one scenario, the fridge is there, loaded with pizza, and you can easily satisfy your craving for pepperoni. But in an alternate scenario, the fridge is gone, possibly stolen by pizza-craving ninjas, and you are left empty-handed. Even though both of these situations are completely different, your behavior leading up to them is exactly the same. In either case, you are still approaching the fridge. This is the key difference with limits. They are used to describe what value a function is approaching. They are not used to describe the value the function actually reaches. Let's see how this works with yet another function. Let's go ahead and use x squared minus 4 all divided by x minus 2. Like before, we are interested in what value the function approaches as we use x values close to 2. Let's go ahead and choose some inputs like 1.9, 1.99, and 1.999. When we use these, we get values of 3.9, 3.99, and 3.999. From these, it appears that the function is approaching 4. So again, we say that the limit of the function as x approaches 2 is 4. If you try and find this value by instead plugging in 2, something strange happens. When you plug 2 into the function, you get 0 divided by 0. This shows that the function doesn't actually ever get to 4. In fact, a quick look at the graph shows a hole right where 4 is. Despite the hole, the behavior of the function leading up to it is the same. Since the behavior is the same, we still say that the limit of the function as x approaches 2 is 4, even though it never actually gets there. Hopefully both of these examples really highlight how limits focus on the behavior of a function, what they get arbitrarily close to. One thing we still have left to cover is what it exactly means when we say that a function gets arbitrarily close to a value. But don't worry, we'll be able to tackle that tricky problem in the next video when we introduce epsilon and delta. Thanks for watching. Thanks for watching.
Actually, you can tackle that when you go to calculus. Okay? We're not getting into that. But does that help you with the limit approaching? Maybe we get there, maybe we don't. And the easiest way to evaluate a limit is to substitute it in. But like he just said, that doesn't always work. And so we need other ways to look at these limits. All right, so now let's look at these this first piecewise function. Okay, let's talk about a piecewise again. I've got these are equations of two different lines, but I don't get the whole line. This line I only use when x is less than or equal to -3. And this line I only use when x is greater than -3. Now I'm going to try to find the limits going to -3 from the left and from the right. From the left, I will actually get there. -3 is part of it, right? From the right, -3, I don't actually get there because it's open, right? But it doesn't matter either way. I can find both limits. All right, so let's look at those. Let me get back. Now, I will tell you, I sort of messed this up first period or whatever earlier today. And so I can't zoom out on this graph because of something I did and the way I'm looking at it right now. And I haven't had a chance to fix it. So you're going to have to take my word on part of it for the answer, but the rest of them will be just fine. But I want you to see that here's -3, right? As I approach from the left, my y value is approaching -2. As I approach from the right, is my y value approaching -2? No, it keeps going off of that you can't see and I can't fix right now. So you're going to have to take my word for it. It's -7. Okay. But you would actually be able to see it on a graph when you're really asked. So my limit from the left is -2. My limit from the right is -7. Okay. Does that make sense? Even though you couldn't see the right hand one, you'll be able to see all the rest of them, I promise. Okay, so I have another piecewise function. We're going to be approaching 0. So when I approach 0 from the left, here's part of a parabola. When I approach 0 from the left, even though I'm coming from the top, my x values are coming from the left, right? Think about that part. So as I come from the left, my limit, what am I approaching when I get to 0? 1. And as I come in from the right, what am I approaching? -5. Exactly. Easy enough from a graph? Okay. Now I'm doing this from -2 for the next one. So, okay, it's the other thing about, see, this one I can kind of control. These little vertical things, ignore them, because if they actually existed, then this wouldn't be a function, right? It's like a glitch in the matrix with Desmos. I don't know why it's there, but it doesn't even happen on all of them. So just ignore the little vertical pieces. But as we approach -2 from the left, what's our limit? -5. Where x is approaching -2, what is y? We're looking for the y value. So as x approaches -2, the y value is -5, right? As we approach from the right, it is 5. Okay, good. So we've got -5 and 5. All right, everybody good with that? All right, so then we have 1 for the next one. What does it look like is happening at 1? On my graph, forget limits and asymptote. It looks like at 1 I have a vertical asymptote, right? Which I do. So as I approach 1 from the left, where's y heading? Infinity. And as I approach from the right, where are we heading? -infinity. Very good. Infinity and -infinity. Everybody good with those? Yes? All right, so now we're approaching -4. What does it look like is happening in -4? Asymptote. And if you're not sure, we can look over here and we'd have to have one at -4 because we know how to find them, right? So as I approach from the left, what's my limit? And as I approach from the right, infinity. Absolutely. So -infinity and infinity. All right, so 6, that's f of x equals secant of x. Y'all know about this much about trig, and you probably never talked about secant, and that's okay. We'll know a whole lot about it next semester. But it doesn't mean we can't look at a graph, right? So this is secant, and we're approaching pi halves, not even 2 or whatever. So when we graph trig functions, we're doing that in radians. I changed your x-axis here, so it's in terms of pi. So if this is 2 pi, this is pi, this would be pi halves. What does it look like is happening at pi halves? An asymptote, right? So same thing, right? Doesn't matter that we don't really understand the graph yet, but there's pi halves. As I approach from the left, where am I going? Infinity. As I approach from the right, -infinity. Very good. Okay. Infinity and -infinity. All right, you good with all that so far? Now let's talk about existence of a limit. This is a one-sided limit. When we talk about two-sided limits, a two-sided limit exists if and only if, so that's a throwback to geometry and biconditional statements. That means you can read it in both directions. But if and only if both the left and right limits exist, all of our limits so far, left and right, have existed. Okay, the limit exists. And not only do they have to exist, but they have to be equal. So if you look at this limit statement as x approaches c, you notice how this doesn't have the little plus or minus on it? Because that just means that whatever that number is in general. This is equal to L if the left one and the right one are the same and they exist and they both give me L. So what all that means is this. Let's go back up to one we already did. Let's go to, let's look at number 3. Okay. Then if I said the limit as x approaches -2 of f of x, I did not put from the left or right, just in general, the limit as x approaches -2. Well, since I was approaching different things coming from different directions, this limit doesn't exist. The left limit exists, the right limit exists, that's great, but they're not the same, so the general limit, the two-sided limit, doesn't exist. Okay, you see how that works? Got to be heading, we have to both be heading to the refrigerator. You can't be heading to the refrigerator and I'm headed to the car. Doesn't work that way. We have to both be heading to the same place, whether the refrigerator's there or not. Who knows if the ninjas have been by and stolen our pizza and our refrigerator? Let's flip it over. Look at the back. We're getting there, all right? Okay, so we have here the one and two-sided limits are all mixed up with some other things too. We'll look at that when we get there. But the first one is the limit as x approaches 2. So that means from which direction? Both, right? Not neither, sorry, not neither, but both. If it doesn't say I have to be approaching, I have to look at both sides. So here's what number 7 looks like. Okay. I'm approaching, oh, what was I even approaching? Y'all tell me, because 2, okay. So as I approach 2, here's 2. Did he took him forever. As I approach 2 from the left and from the right, do you think it's going to exist? No. Yes. Am I approaching the same thing? Yeah. Yes. Now, when I actually get here, it is undefined, right? Like, so if I was to substitute it in, it would be undefined, right? So the substituting in isn't going to work here, but because there's a hole there. In Desmos, it doesn't really show that it's a hole. It just shows that it's undefined when you click there. But as I approach 2 from the left or from the right, what's my limit going to be? -2, because it's the y value. You'll have the graphs will be there for you. Like, you won't have to type them in. You won't. Yeah, that's a very good question. No, you don't need Desmos for this, because in Delta Math, where your assignment is, they will give you the graphs, and so you can tell from there. That, because I didn't want your assignment to be 30 pages either, because you'd have to have big graphs to be able to do that. And I also didn't want you to have to type them in, because that takes forever. Okay, it was just easier to do this way. Okay, so now we're approaching -1 from where? The right. Okay, so we're going to approach -1 from the right. What does it look like is happening at -1? Asymptote. And if I substitute -1 in here, would I get 0 in the denominator? Yes, so it definitely is. And we're approaching from the right, so what's my limit? -infinity. Very good. Yeah. All right, now we're approaching -4. From which direction? Both. Yes. What? Exactly. Well, the 4 is negative, but I don't have a little negative like up in the exponent. Okay. Good observation there. Okay. All right. So now, -4. Does it? I have no idea why this is here, but does -4? What does it look like? I have an asymptote there. You sure about that? No. At -4, look what's happening. At -4, I actually have a point on my graph, right? It's actually undefined, but -3 is actually the asymptote, which, again, I know sometimes you have to kind of guess. We could factor all that, but if I just go straight up from there, I have a point there. If I go straight up from 3, if I did, it would be way up there. I don't know why sometimes I click on it, magically appears, and sometimes it doesn't, but there's my well, see, I don't even know what I've been doing. It just was like, whatever. But it was there and then it disappeared. But -4 is not the asymptote. So here's why I put this question on here. Don't fall into the trap just because the function has an asymptote. Don't assume that that's the limit you're looking for, because that's easy to kind of fall into that trap, all right? But as I approach -4 from the left and from the right, even though it looks like I'm coming from the top, x is coming from the right, right? What am I approaching? X is approaching -4. What's that y value? +4. The x value is -4. The y value is +4. Okay? This is your x value. Your answer is the y value, the output. Okay? We good so far? All right. Now the limit as x approaches 3 from which direction? Both. You'll get it. It's okay. That's why we're doing so many. What does it look like is happening at 3? Asymptote. And if I do that, I can tell, I mean, it is. So from the left, what am I approaching? From the right? Positive infinity. So what's my answer? D and E does not exist. Okay, listen. In order for the limit to exist, they have to be approaching the same thing. The left is approaching one thing. The right's approaching another. Does not exist. That's for me. Oh, thank you. Right? That's nice. We'll look at that in a minute. All right. I don't know. I don't know. No, we're gonna finish this. Oh, I know what it is. It's from Miss McWhorter. Did you all have Miss McWhorter last year? Oh. I let her borrow. Okay, hang on. Oh, do they? Yeah, love her. We all love Miss McWhorter. All right. So number 11. We're approaching 0 from which direction? The left. It's okay. We got it. We got it. All right. As I approach 0, yes. So as I approach 0 from the left, -50. -50. Y'all are so silly. Everybody's been silly today. It must be a full moon. I don't know. You sound like that little Peppy Pill. Did they record you for that? Because that's pretty funny. See? Look at it. Good Lord. Am I going to get y'all back at all? Take a deep breath. We're almost done. All right. As we approach 1 from which direction? Both. Very good. And so as I approach 1 from the left, from the right, so what's my answer? Infinity. Okay. Now I might break your heart a little bit here. We're going to put a little star here because there's a little side note to that we'll get to once we get to talk about the bottom. Okay. Well, the very bottom of the notes, we're going to come back to this. We'll revisit it. All right. 13. 0 from which direction? The right. Yeah, I know. Well, you can look at your, I know. It's very hard to see. I'm coming from the right. So 0 from the right. Where are we headed? Infinity. Good job. All right. 14 from which direction? Both. So what do we think? D&E. Good job. D&E. Because they're heading, okay, for those of you that weren't part of the game there, it's because we're heading to different things, right? Everybody understand why? Okay. Silliness. All right. The left. 5 from the left. Goodness. All right. Left, left, left.
What? Negative infinity. Negative infinity.
As I approach 5 from the left, -1. Do we know why?
Yes.
Yes, we're all good? Okay. All right. 1 from which direction? Both. Okay. We're heading to 1. I know there's only one side, but I'm heading to 1 from the left and from the right. Okay? And so when I get here, if you can see the numbers, well, my hand, it flips around. And yeah, we're getting really close to 0.5. I also put a little chart here because you could be asked this from a table. And if I substitute in 1, I'm going to get undefined, right, because of this. But if I put in 0.99 or even more than that, and then 1.001, so I'm really close on either side, you can see that we're at 0.4999 and then 0.500. So those are, we're squeezing in to get to 0.5. Does that make sense to you? If y'all remember on one of the first assignments you had, it was one of the rates of change. And we plugged some stuff in the calculator, and then down at the bottom it had that weird question none of y'all knew how to answer because I forgot to take off. And I was trying to get you to this, that if those numbers ended up correctly, they were getting closer and closer to whatever it was. Let's just say it was 0.5. And it was kind of the idea of a limit. It was just way too early to talk about that stuff, and I meant to take it off. But do we see how we're just looking at how we're approaching that? Okay. So this is 0.5. All right. 17 from what? The 2 is negative, but it's both directions. Okay.
Negative infinity and -1.
-1 and 3.
Wait, what?
All right, check this out in case we need the one-sided. As x approaches -2 from the left, the limit is -1 because the y value is -1. As we approach -2 from the right, the limit is 3. They're different, so my answer is D and E. Okay. Do not enter. Right.
So
does not exist.
where it has like that end is where it's going to?
Yes. All right. Now, every piecewise function we've done so far today has been like, there's been a jump and they've been different, right? That doesn't necessarily happen for all of them. Now, on 18, we want our limit from which direction?
Right.
The right. Okay. So let's do that, and then we'll talk about this one a little bit more. As I approach -3 from the right, what's my answer? 0, because it's the y value. Now, if I asked you the limit of -3 from both sides, would the answer still be 0 here?
Yes.
Yes, because even though it's a piecewise, they snap together, and that happens sometimes, okay? I don't want you to think there's always a jump. All right, so what was it, 0?
Oh, this isn't even a real unit. I think the one time I'm doing good.
But that's okay, because then the next couple lessons will make way more sense. You'll feel better about it because we don't have to get into the weeds of this. If you understand this, the next part will be fine. Charlotte better watch this video. Everybody say hi to Charlotte.
Hi, Charlotte.
And we'll know if she doesn't watch this video, because then she won't make it. She won't tell us that we said hi to her. Okay. Now, how do you approach negative infinity?
Down.
From which direction?
Down. Left. Wait, what?
Okay. If I'm approaching negative infinity, I can only approach from the right? Because I can't get on the other side of it. So, but notice there's not a little plus or minus, because this really isn't left and right limits. If I'm way out here, what do we also call this? End behavior. And our end behavior we've already done. How did we determine that? By looking at what part of the function? Kind of, yes. To give us the horizontal asymptote, right? Because way out here, we're approaching the horizontal or the slant asymptotes, right? And yes, we had to look at all that stuff I just heard. So that's good. So even before we look at a graph, then we can look at this one. Is this top heavy, bottom heavy, or tied in degree? Bottom heavy. So where is our asymptote?
0.
It's at y equals 0. So if my asymptote is at y equals 0, What are we approaching way out at the ends? 0. Just 0. Which we've already done that, right? And I put that in here so that we kind of talk about it all together. And we didn't look at a whole lot of graphs. I'll show you the graphs. As we approach, I know, the rational functions can be some pretty cool graphs. And if you weren't sure, like, I don't know. It's like somebody turned on the radio. Clearly I have an asymptote, right? But who knows if maybe it's at negative 0.1 and we can't tell. But we can tell because we know how to look for the asymptotes, okay? So I don't care about this nonsense going on. It's kind of cool looking, but way out there, we are approaching 0, okay? So let's look at 20. Top heavy, bottom heavy, tide and degree. Bottom heavy. So what's our limit? 0. As we approach infinity, it's 0. If I was approaching negative 2 or 3, then I look at the middle behavior. If we're talking in behavior, we're talking asymptotes, okay? All right, so let's look at that graph. Here's this one. I know. So we know we have an asymptote at y equals 0, right? Here's an instance where the function crosses the asymptote. But that's middle behavior. We don't care. Way out here, we're approaching 0, and that's what we're interested in within behavior. Okay? We good on that? All right. All right, number 21. Top heavy, bottom heavy, tide and degree. Top heavy. By how much? 1. So we have a what? Slant asymptote. You have a, what did you say? Listen. Okay, I didn't hear you. That was okay. What did you say? What did you say? Oh, A over E. Oh. Well, sort of. We're going to do this. So yes, that too. So when I divide that out, so basically I have y equals negative x cubed over 2x squared. And when I simplify that, that gives me negative 1/2 x. Okay? Now that part's important because I have a slant asymptote. That's not my actual slant asymptote, but it's parallel to it, right? It gives me the first part of it, which means I know that my slant asymptote has a negative slope, so it's going to look like this. Since my slant asymptote looks like this, if I'm approaching infinity, as x approaches infinity, what is y approaching? Negative infinity. Okay, that's how that slant asymptote helps me, even though I don't divide it out and find the whole thing. I don't need it. Okay, so let's look at the picture. Here's my function. Ooh, yeah. But do you see how the slant asymptote would live in there? And then as we keep going to infinity, the y value is just going to keep going down to negative infinity. Okay, but I don't have to necessarily understand the graph for that because I can just look at the function and depending on what's been given to me. Okay. Top heavy, bottom heavy, tide and degree. Tide. Okay, equal. So that means I do the ratio and my answer is going to be 1/4. Right? So let's look at that graph. If all I had was the graph, maybe the asymptote is at y equals 0. If all I had to look at was that, because remember, we can cross it and then I could still approach 0 from the top. But so, you're kind of guessing if all you have is the graph, but we know enough about asymptotes, we can look at this and it's actually at 1/4, okay? Which makes a little bit more sense on that one. All right, good deal. Top heavy, bottom heavy, tide and degree for 23. You look at the highest exponent, that is tide. Turn back around. So then what is my limit? Negative 5.
We're going to dismiss freshmen.
Look at the next one. Top heavy, bottom heavy, or tide and degree? Tide and degree. So what's my limit? It's the ratio. And what would that give me? Negative 5. Good. Because I'd have the 10 divided by negative 2. That's negative 5. So that's where my asymptote is, right? What? You good? Oh, I skipped 22. I'm so sorry. No wonder. I was like, why are y'all giving me weird stuff? I don't know why I skipped 22. We'll go back to 22. Let's go ahead and do 23. I just got ahead of myself. So yeah, 23. And then we'll go back to 22. I don't know why I skipped it. I didn't mean to. But you see here how we have a horizontal asymptote. So as we're approaching whatever it said, no? Either one. I'm approaching negative 5. Now look at this point here. What is this point? Like what kind of point is, what will we call it? It is the y-intercept, and it's also what? Point of inflection. Good. It's both of those things. And so, and y'all, those confuse you sometimes. It's not a maximum or minimum, right? Because I'm not changing from increasing to decrease. I'm increasing the whole time, but I am changing from concave down to concave up. Okay? So make sure that you get that. All right, let's go back to 22 that I totally skipped. That one's also tied in degree. And tied in degree, and what would we be? 1/4. Good. We'd be approaching 1/4. Let's go back and look at that graph. And see here, without knowing that, I can't tell, maybe my horizontal, just from the picture, maybe my horizontal asymptote's at 0 and this crosses it and comes back down. You know, you really can't tell by just looking at the graph, but we do have enough knowledge to know it's actually at 1/4. All right, good deal. Then one more of those. Top heavy, bottom heavy, tied in degree. Top heavy. Do I have a slant asymptote? No. But if I make that ratio, I will get y equals 5x squared, right? So that means that my asymptote is a parabola. So whether I'm approaching infinity or negative infinity, what's my limit? Infinity. Good. And then I will show you the function, which the function kind of looks like a parabola, doesn't it? But it's not. You see how it's kind of flat on the bottom? So it's not a parabola. It has parabola-like looks, but the asymptote for sure is parabolic, so it's not going to touch that. Okay? We're good on all those? Let's talk about when the limits fail to exist. Okay? So a limit can fail to exist under any of the following conditions. If the function contains a jump, which is called a jump discontinuity, therefore it approaches a different number from the left side or the right side. So basically that's just from the definition of a limit. If I approach different things, I'm not going to have the limit. And I don't know how well it shows up on your paper. It doesn't show up here well at all. But I have this with an open circle. I have this with a closed circle. Okay, so clearly there's a jump. I'm approaching different things as I approach 0, so that does not exist. Okay. Then if the function contains a vertical asymptote and therefore increases or decreases without bound as x approaches c, so as x approaches -2, I'm going to negative infinity and infinity. Again, basically just approaching different things. And so it doesn't exist. This is why we put the little asterisk up there. Because technically, by definition, this doesn't exist. Even though this is the one that looked like this, because we have that vertical asymptote and it's a discontinuity there, even though we're both going to infinity. So the way around that is when we get super technical in future courses, we're not going to get super technical now, we would say things like, when it asks you for the limit, you would just say the function increases without bound, which is, I know, sounds like the same thing as approaching infinity, and it kind of is. It's just, again, one of those technicalities. Like technically, nothing can equal infinity because infinity is not a number, but we don't get that technical with our notation in pre-cal because we're trying to understand things. So I always feel like I should kind of throw those things out there because in the future, if you're like, people are telling you, you take other higher level classes and you can't do that equality or whatever. It's just, we get to be a little bit lazier with it now because we're just learning it. All right, and then our last one is when it oscillates. Now, oscillating in general is just going back and forth like this. It's kind of like a sound wave. But if you notice here, it's going back and forth, but then it gets like real crazy and real crammed together. So it's jumping back and forth so quickly as we're approaching 0 that you can't nail down what the limit is. And so this one does not exist. This particular one won't come up that often for us. These two will, but again, it's really just we're approaching different things, and then it doesn't work. Okay? We good so far? Yes? Awesome. Where's your assignment? Delta math. Okay. And also your, like I said, I will assign these graphs so you can go back and look at them if you need to.